Hello, I'm Michael O'Connell, and in today's video, we're going to be performing a von Neumann stability analysis to investigate the problem we encountered in the previous video. Specifically, we want to find the limit of stability on the explicit differencing method that we have been using to model the temperature profile of our bar. Here is the heat diffusion equation that models this situation in which we are heating our bar up, and this equation right here is the solution to this partial differential equation. I'm not going to discuss how this solution is obtained because it would take too long, and that's not the focus of my video. So I do want to mention that this solution has this value k. K depends on the boundary conditions. So the overall solution is a summation of functions that look like this. And you would have acceptable values of k that depend on your boundary conditions. So do you have one side of your bar insulated, in which there's no heat transfer, or do you have one side of your bar set to a specific temperature? In our case, we have each side of our bar set to a specific temperature value. So those would dictate the acceptable k values for a solution to this differential equation. Now, what we are going to do is use this solution to perform the von Neumann stability analysis based on the explicit differencing that we performed before. So we had this equation in the for loop in the previous video, and this equation was used to compute the new temperature values at all of our position increments, okay? So that is what I'm going to write on the board here. And we want to use this solution to perform the von Neumann stability analysis and find what the limit of stability is. Because remember, what we found is that when our time step was greater than this 0.5 seconds, the graph looked crazy, okay? So there is instability when that value is greater than 0.5 seconds. And what we want to do is use the von Neumann stability analysis and see what's going on. Okay, see if that's actually the case and figure out why there is some limit on the stability of that explicit differencing method that we have been using. So enough chit chat there. I'm going to write this expression that if you've watched the previous video, you should already be familiar with. Now we're ready to work on the right-hand side of this equation. So let's describe the temperature at some position j and at some time n using this solution that we have. Now, what is x and what is t, right? This will depend, of course, on this equation that we already have. So we have some position step, delta x, and we multiply that by our index j, okay? So that's our expression for x. So hopefully you remember that from the previous video. And then we had something similar for time. Again, we use this index j and this index n to keep track of where we are. If it's j, it's in terms of position, and then if it's n, it's in terms of time. Okay. So again, we had our time step delta t multiplied by some index n to describe how far we've moved in time for the heating up of this bar, okay? So that is going to be important when we write this expression, okay? So we would have E, I, K, and then J delta X, right? And then similarly here we have negative alpha, we have the K squared still, and then N delta T, okay? Now we have a few other different terms here. We have j plus 1 and j minus 1, of course, at the same time, n. So how do we deal with that? I'm not going to be lazy here. I'm actually going to write out this one, okay? And then I can be lazy with the next one. So, and you'll see why. So here, it's actually j plus 1 delta x, and then n, of course, is the same. So what can we do here to simplify things? What's really nice is we can express this in terms of t sub j comma n. How can we do that? Well, we already have that common j term, okay? So we would multiply that delta x n, but we do have this plus 1, okay? So that means that all of this, I don't know how to include all of that, that will be its own separate term, but everything else is the same as t sub j comma n, okay? So I'm going to write that, and I think if you just take a second to look at it, you'll be like, oh, that's pretty obvious. So it would be the same thing, except you'd have ik delta x times t sub j comma n. So hopefully you see how that makes sense. Again, this isn't j, this would be j plus 1 here. The plus 1 would include I, k, and delta k. And again, we're at the same time n. So that is all included here in the t sub j comma n. And then you have the extra Euler's number raised to the I, k, delta k power multiplied against the t sub j comma n. Man, that is a lot of words there. Fortunately, this one I'm going to be lazy with, because we have the negative one. We know that that would just be negative I, k, delta x times t, j, comma n. It's hard to write down here. So hopefully, I wonder if that's even visible. Okay, it's more visible than I thought, but I'm not making good strokes down there, so it's hard to see. But these, of course, are important. I'm going to take some time to erase, and we are going to use these to rewrite this part of the equation. Notice that I factored out the common term, t sub j comma n, okay? And again, that's the temperature at some position increment at the current time. And then this equation is awesome because it relates that to the temperature at the same position at the later time, okay? So that's why we were after this t sub j comma n to begin with. Now, we want to get at these here because they have the imaginary number I. And we can use that using Euler's formula, which looks like this. You may have seen it before, okay? And you might see where I'm going to go with this, right? Because we have Euler's number with a positive exponent and then Euler's number with a negative exponent. So we can look at e to the negative ix, okay? And a cosine stays the same, right? It's an even function. And then this is minus I sine x here, okay? And notice that here in this expression, we're adding these terms together. So we can add these together, okay? Those go away, and you're left with 2 cosine x, where x is just whatever is multiplied against the imaginary number in your exponent, okay? So for us, that would be k delta x, okay? And also, don't forget about the constant r that we have to think about as well. Okay, so we're going to get a new expression here that I want to talk about. Okay, once again, we're at the same position j, and then we have this expression that gives us the temperature at the later time. Okay, we have the 1 minus 2r here still, and then now we have plus 2r cosine x is delta. Okay, that's our position step. So we have delta x times k. Now, this expression for the von Neumann stability analysis, this cannot be greater than 1, okay? Because if it's greater than 1, as we go to the next time step, to the next time step, this can get extremely large very quickly, okay? Or it can get very, very small very quickly. As we saw with our graph, that was very unstable, right? We had values shoot up very high and then very low at a certain frequency, okay? So that was the craziness that we saw in Python when we made our time step greater than 0.5 seconds. So again, that's the key to the von Neumann stability analysis, is that the absolute value of this term, right, needs to be less than 1. So let's see what the limit of stability is for the explicit differencing method. Remember that in this method, we described the second derivative with that difference. That was back in, actually that just was the second video, because the first video I did in this series was just about getting the heat diffusion equation for a Cartesian coordinate system. So again, you can actually just watch the last video to see what the explicit differencing method actually looked like. Okay, so we can actually find out what the limit of stability is for such a method, right? So we have 1 minus 2r plus 2r cosine k delta x. Okay? And this expression here, we don't need that extra parentheses. Must be less than or equal to 1 or greater than or equal to negative 1. I took some time to erase everything, and then I rewrote the inequality up on the top here so that we can continue our evaluation. So let's subtract 1 from both sides. This 2r is a common factor, so we can pull that out there. Notice we still have the cosine of k delta x and then minus 1. Okay? And this is a 0 over here. Notice that this term here, the cosine, is always going to be less than or equal to 1, right? So if this is less than or equal to 1, then this whole term is always going to be negative. And then we have r. R is this, the thermal diffusivity multiplied by our time step divided by our position step squared. These are all constants that are positive. So r is always going to be positive. Therefore, this entire term in the middle of our inequality here is always going to be negative. It's always going to be less than or equal to 0. So we can get rid of that over there. Okay? Let's divide both sides by 2. And let's divide it by this term. I'm going to flip the sign here and flip the inequality as well. So dividing by 2, this would be negative 1. But as I said, I'm going to flip that around. So this inequality sign is going to go the other way. We have 1 over. And then we have our, whoops, sorry. We're flipping these two terms, right? So hopefully you understood that. I divided both sides by 2, and then I divided by the negative value of this term here. Okay, so hopefully that wasn't too confusing. That's why that negative sign would have gone away up here. And we get this expression with r. Okay, let's think about this here. So obviously, cosine of anything at its highest value, I'll just use cosine of x here. At its highest value, it can be 1, of course. If it was 1 in this case, this will go to 0. So this von Neumann stability analysis would be telling us that our r value must be less than or equal to infinity in order to maintain stability. But of course, that's absurd because that's as non-stringent as you can be. That doesn't tell us anything about the stability of this explicit differencing method that we have used. So the alternative here, of course, is that this cosine value can become negative 1, right? So 1 minus negative 1, of course, is 2. And what do you know? This tells us that our constant r value here must be less than or equal to 1/2. And that is actually consistent with the observation that we made in the previous video, where our time step, clearly, once this was above 0.5 seconds, we were unstable. Okay? Why was that? Well, remember what r is. R is alpha delta t over delta x squared. And these two terms, these were 1. Okay? So r effectively is equal to our time step. So that's why this is our limit of stability for the explicit differencing method for this problem. And more specifically, it just verifies and supports the observation that we made in the previous video where we increased our time step above 0.5 seconds and our solution went crazy. The graph was insane. Okay, so that is our limit of stability. So I hope you enjoyed watching this video and came to understand a lot more about the von Neumann stability analysis and its utility in supporting an observation we made in which the method that we used, the explicit differencing method, was unstable at a certain point. Because if you wanted to increase your time step so that you can save yourself computing time, you could encounter problems, because if your time step was too big and you use the explicit differencing method, then you are not going to get a good temperature profile of the situation in which you're heating up that bar. So I think that this is extremely important. So we are going to keep working on this problem, and you will have to watch the next video to see what we do next. Thank you so much for watching, and I hope to see you next time.